Welcome, geometry students, to the lesson for 12.4. Today we start looking at volume instead of surface area. We've been looking at surface area the past couple lessons, but today we're going to focus on volume of prisms and cylinders. So make sure you know these things by the end of the lesson here, and check out those extra examples in your book. So we've got some different prisms and cylinders drawn here. We're going to draw our own versions of these things later on. But to start though, a postulate that comes up in the beginning of this lesson, something that we should know from previous math classes, but the volume of a cube. There's a shortcut formula for that. Yes, it is just length times width times height, but since they're all the same, we can call them all S for side length, and we can just say that the volume of a cube is S cubed then. And so the volume of a cube, what that looks like, this is postulate 27, by the way. We'll bring up the book in just a second here, but you have a cube. So to draw a cube, I think the easiest way to do that is either to draw a square here and then another square kind of behind it, connect the lines, and then make the appropriate ones dashed, or you can just draw the square, draw lines at about a 45-degree angle going back that are the same length, and then make your dashed lines after that. So that's the volume of a cube. If you call each one of these sides S, they're all going to have the same side length. So we can just say it is x squared, or S squared. If you want to see an example of this, let's write this in a different color. For an example, you can see example 1 on page 743. I don't feel like we need to go over one together like that in full here, but we will check it out in the book just a second. And so here is 12.4. We're looking at the volume of a cube. There's some other things too. If two polyhedra are congruent, they have the same volume. I think that makes a lot of sense. It's a postulate though, so we're not proving that that's true. Volume of a solid is if some of the volumes are it's non-overlapping parts. So if you had this kind of weird looking shape, but you could find the volume of individual sections of it, and you put it all together, you have the volume of the whole thing. That's another way to say that. Yeah, example 1, the volume of a cube or a box, you can use the idea of length times width times height, or side times side times side if they're all the same. It's actually not example 1, well, sort of it is. You got the volume of a unit cube would be 1 times 1 times 1. So this is a cube. This actually is a rectangular prism though. So this one you'd have to use length times width times height, which is base times height, but we're getting to that. So I'm kind of getting ahead of myself a little bit there. So let's get to that here, and let's put up here, these are the volume theorems. These are the big guys for this lesson. So this one over here is the volume of a prism. And we've talked about prisms. Prisms, remember, it could be like this one, like this one, like this one. You have a triangular prism here, a rectangular prism here. You could draw in the dashed lines right there, and a pentagonal prism or pentagonal prism here. Tomato, tomato. Do you know of anybody that pronounces tomato, tomato? I've never heard anybody actually seriously pronounce tomato like that. I don't think that's right. I think we should come up with something else. More like car or car. I'm going to drive my car if you're from Boston. You've got a triangular prism here. You've got the two bases here and here. You've got a rectangular prism. You could call the top and the bottom the base. The base, remember, bases are the parallel parts. Here the pentagon is parallel with this part over here, and they're also congruent to one another. This is a cylinder. We're getting to that in a moment. But the volume of any prism, volume is actually, in my opinion, easier than surface area. I think considerably easier most of the time. It's just base, the area of the base, times the height. If you're talking about a rectangular prism, then the base is just the length times width of the rectangle. If you're talking about triangles, you'll have to find 1/2 base times height to find the area of the base. Sometimes there's equilateral triangles. We can use that shortcut formula. If you have different shaped bases like a pentagon, a heptagon, octagon, you're going to have to use that apothem method to figure out the area of the base. So we've been reviewing that a little bit, as we've been going along with this chapter. But let's draw some pictures here. This is the important thing to remember for the volume of a prism. We could have different kinds of prisms though, so I want you to draw, we're basically going to draw these three things, or these types of prisms, just as examples. So these are some examples of prisms you might have. So this would be a rectangular prism. This is rectangular. You could have a triangular prism. I'm going to do a little different one than that. That is also a triangular prism right there, but let's say I had something like that, and I'd have to draw a parallel part to that. So I'm going to draw a congruent triangle to that at the same angle. I'm going to erase some of this in a second. It's not my best job with that. I got to keep that on the same angle. It's a little better there. Okay, now these would connect here and here. This one's going to be hidden. You wouldn't be able to see that, and then I would make these ones hidden as well. Just erase the little parts here and here. So there's a triangular prism example. This is another triangular prism example. That's triangular. You could have a pentagonal prism like that. The bases wouldn't have to be here and here. They could be on the top and the bottom, and so here's one where I have it like that. You can also draw prisms like this where you make the length of all the lines going down or up this way if you're drawing it that way, the same length, and then you connect all those, and then the hidden parts that you can't see, draw dashed lines for those. So another way to approach drawing these things, this would be a pentagonal prism. So some examples of prisms there. We'll check out an example of using actual numbers in a little bit with that. But then a cylinder, the volume, it's still the same idea. It's still the area of the base. You've got a base here. This, you can't see that, but it would be a circle back there. You'd have a base right there. You've got the area of the base times the height. And so no, you are not allowed to leave your seat right now, even though the bell's ringing. So the area of the base, being a circle, that becomes pi r squared, because the area of a circle is pi r squared. So you have pi r squared h. This is really what you should remember for a cylinder, what you need to use. But you can remember this is the same as this, and then derive the formula based on the fact that it's still base times height. So let's write this, or equivalently this. This is more what I want you to remember though. And so let's draw a picture of a general cylinder. And make some dashed lines there in our different color. Over here, let's put B's where the bases are, and let's put an H for the height. Here's a B, here's a B, here's a height. This one, this happens to be the base, this is the height. Over here, you'd have a radius, and you'd have a height for the cylinder. And now let's check out some examples, but one more thing to insert into here, something called Cavalieri's principle. And this is theorem. I went out of order a little bit here, but that's okay. This is theorem 12.6. So theorem 12.6, Cavalieri's principle. It shows you some examples here. If things have the same height and the same cross-sectional area, so they're saying if B is the same, the area of the base here is the same as this one is. Notice this rectangular prism is kind of just got pushed over on its side. Imagine somebody pushing a stack of paper, maybe you have computer paper over. It's still going to have the same volume, even though it's on a slant. That would also have the same volume as something that has a cross-sectional base here that is equivalent to this one, even if it's a circle or a different kind of shape. As long as the cross-sectional areas are the same and the height is the same, all three of these would have the same volume. You could take a stack of pennies. We might do this in class. Take a stack of pennies or coins. If you push it off to its side, you still have a stack. It's an oblique stack now, but it still has the same volume. It still would take up the same amount of space. So that's what Cavalieri's principle says, and we'll say, let's write this down. There's a picture on page 744. If you want to write that down or draw the picture later, you can. But what it says is that if you have two solids, that have the same height and the same cross-sectional area. At every level, we'll say. So going back to the picture here, saying this would be the same cross-sectional area as the top, any level you pick, maybe right here, maybe down here, the bottom. All these cross-sectional areas would be the same as you went along there. Then they have the same volume. So you might see a couple problems about Cavalieri's principle as well. But now let's get into some examples where we deal more with the meat of this section, the volume of a prism and the volume of a cylinder. So let's check out one. Let's draw a triangular prism, but this one's going to be kind of standing up on its side. So triangle like that, go back the same length each way here, here, and connect that, and then we're going to have one more same length as these ones were, but dashed. This is going to come down like that. Okay, and so now we've got a triangular prism. I'm going to tell you that this is a right angle, so you can include that in your picture. I'm going to tell you that this is 6 millimeters. Down here is 2.5 millimeters. It's a 5 right there, and this is 3 millimeters. And so we're going to be using, we're trying to find the volume. We're going to be using that V equals B times H. Now what are my bases over here though? Let's put this in our different color. Identify the bases. The bases are parallel to one another. They're in parallel planes, and they are also congruent to one another. You have rectangles. You've got one here, here, and here, but none of those are your bases. They're not parallel to each other. They're also not congruent to each other. The triangles are the bases. So capital B here, capital B here. We're trying to find the area. That's what this is standing for, the area of the base times the height. So the area of the base would be, it's a triangle, so we're going to have 1/2 of the small base. The little base would be 2.5 for that triangle. You could use that times the height would be 6. You could flip-flop those numbers as well. So we'd have 1/2 times 2.5 times 6. That's going to be the area of the base, which is a triangle. That times the height. The height is the part connecting the two bases, which is 3 in this case. So we have times 3. So from here, let's work this out. We've got 1/2 of 6. That would be 3. 3 times 2.5, that would be 7.5. So we have 7.5 times 3 now. If we simplify that, we've got our final answer. That's going to be 22.5. Now this is volume, so we're going to be using our units as millimeters, but this time instead of with surface area we were doing squared because it's a unit times a unit. Here we're doing a unit times a unit times a unit. We're doing millimeters cubed, in other words. So volume is always your units to the 3rd power. It's always units cubed. You're multiplying 3 units together. Let's move on to example 2. Let's check one out with cylinders now instead. So draw a cylinder as best you can. We'll just freehand these things. Maybe we'll have a contest later who can draw the best freehand cylinder. I had a geometry professor back in college that was just incredible with his freehand drawings. I think he would beat any of us. Professor Venema. Brilliant guy. He wrote his own geometry book for our class. He wrote the textbook. That was pretty cool to have a teacher that wrote his own textbook for the class. He's very aware of what was in it, that was for sure. So we have the volume for a cylinder. It's still capital B times H, but the base now is pi r squared because it's a circle. So let's put that here. Let's put B here and here in our different color. Let's label that with an R right there. That's my radius, and then this is my height right there. And so from there, plug the numbers in. So volume is going to be pi. Leave pi as pi for now. Let's not round it off yet. And R is 4. So we've got 4 squared times 13. That's going to become pi times 16 times 13, 16 times 13. That's 208. So you have 208 pi. This would be an exact answer. So this would be acceptable if they didn't say to round it off. You could say this is the final answer. So that many feet cubed. If you were to round it off, though, we would take our calculator out. We would multiply 208, multiply that times pi. So we have this times pi here. That would give me, use the pi button on the calculator for the best answer. Don't use 3.14 because that won't give you as good of an answer. 3.14, did I say 3.4? I may have, I don't know. 3.14 is an approximation. Use the pi button for a better approximation. So we get these answers. This would be exact on the top and approximate on the bottom. So it just depends on the situation and what the question asks for. I rounded to 2 decimal places, but you may want to round to a different number of decimal places. Just read the directions and see what it asks for. So from there, you've got your volume of a cylinder. So those two pretty straightforward. The next two, a little twist thrown in the action here. So on this one, we are going to solve for x. So perhaps you know the volume of something, but you don't know one of the measurements. We can use this concept, this idea, to find the missing measurement, the missing maybe length, width, or height. This is a rectangular prism, so we're going to be using that idea. So it's still b times h, but your base now is going to be just a rectangle, so you can just use length times width times height. That's the idea here. It's the same formula, same thing you learned from previous classes. You can still think of it like that. So here's x centimeters. That's going to be my missing measurement here. I'm going to say that this is the same measurement, x centimeters as well, for the width and the height here. And I'm also going to tell you that this is given to you. You are given that the volume is 396 centimeters cubed. So how do we do this? Well, let's use our same formula again. We've got b times h. You can say this being a rectangular prism, you can use this as well. Or length times width times height, since it's a rectangular prism. So let's make a little note of that in our different color off to the side there. So from there, your base would be 11 times x. Let's put that in our different color too. Let's use this and this as our parallel parts. These are congruent rectangles that are parallel to one another. That we'll say is our base. We'll have 11 times x. That's like our length times the width times the height is going to be x as well. And so I know that this is supposed to equal, though, 396. So I'm going to put that right in there. And let's use our different color for this as well. Let's plug that, or show that we plug that in right there. So that's where that came from. That number came from the fact that we were given that number right there. And so we have 396 is going to equal 11 times x would be 11x squared. And then show these other steps in your different color. Divide this by 11 to get x squared by itself. That's not going to be x, but it's going to be x squared. And 396 divided by 11, I don't know that one off the top of my head, and I'm just going to double check my work here. Yep, it is 36. So that's going to reduce down to this. And then you would take the square root of both sides to get x. We would definitely take the positive square root value of this, since we're talking about lengths and widths and heights. We're talking about dimensions. That x squared will cancel, the squared will cancel with the square roots, and this will be x equals 6, and you could say 6 centimeters as well. So 6 centimeters is your answer. If you take 11 times 6 times 6, plug that back in, you can check that very easily. You'd get 66 here. 66 times 6 would in fact be 396. So a quick way to check your answer. Put a little period there. I think we're good to go with that one. And example 4, let's check out a cylinder now where we have a missing measurement. So cylinder, draw Good freehand cylinder as best you can. And let's say now that all the way across, we're going to say is x feet. So we're going to try to figure out what that is all the way across. There's the center of my circle there, and let's say this is 5 feet for the height. And I'm going to tell you that this is given to you. That's given that the volume equals 277 feet cubed. So here, being a cylinder, we're going to use still base times height, but the base is a square, so pi r squared times the height, pi r squared times h. We know that volume is 277, so let's use a different color just to show where that came from. Right there. It's coming from right there. And your pi, we know what pi is, but we don't know what the radius is. So I'm going to leave that as r squared. I do know my height, though, is 5. And so from there, I could rewrite that. The more normal way we would see that would be 5 pi r squared. We'd put the coefficient in front. From there, you can divide by 5 pi, because we want to get r squared by itself. We want to get r by itself eventually, but we've got to get r squared by itself first. So we'll have 277 over 5 pi would equal r squared. Now I want r by itself, so I'm going to take the square root. The square root will cancel with a square. So you're going to type all this into a calculator all at once. I want you to be careful, though, very careful when you do this. Let's put this even in parentheses down here. If you don't put that in parentheses on a calculator, seeing that your calculator knows order of operations, it would take 277, divide that by 5, and then multiply all that by pi if you did not put this in parentheses. So be careful. I'll show you here what I'm looking for. I'm going to do 277 divided by 5 pi first, and then I'll take the square root of that, since it's not as easy to see everything I type in here. So let's do 277, no, one too many, divided by, and then I'm going to use parentheses, otherwise it's going to divide it by 5 and multiply it by pi. So I want to take 5 times pi first. So close my parentheses. Now it's got 5 times pi, does that, and then we've got 277 divided by this. This 5 times pi is this number, so I have to hit equals one more time. I've got 17.63, and now I want to take the square root of that number. So I'm going to hit, where's my square root button? On here, there it is. So I'm going to take the square root of that. Now I've got about 4.2. If I round that to 2 decimal places, 4.20 would be what I have. And so this would be 4.20. Use my normal color for that. There we go. So 4.20, and this is the radius, approximately what the radius is. But x is, notice, the diameter. So we're going to take this value, and we're going to say that now, so the diameter is approximately 4.2 times 2, which is going to be, this is equal to x. The diameter is what x is. So we have 8.4 is approximately what x is. This is 8.4 feet. And to cap this off here, let's take a look at example 4 in the book. Notice you can use this for some real-life applications. Volume and surface area have tons of real-life applications. You'll probably use those ideas at some point in your life, no matter what career you end up choosing. Volume, surface area, somewhere you're going to use that. You're going to use a recipe. You're going to have to find a certain pan that's a certain size for making recipes. You might have to fill in blocks like this, use concrete blocks. You might build something someday. You're probably going to use volume and surface area. You might paint something. You might need to know how much paint you need to paint the walls. You might fill in something with sand or concrete or something like that. You'll need to know how much cubic yards of material to buy. Volume right there. So lots of real-life applications with this material. This concrete, you can take the volume. You can take the volume of the whole thing, the whole big box rectangular prism. You can subtract these smaller rectangular prisms from it, and you're left with what you see here, what the actual concrete brick would be. So they do that because they're saving concrete, and it's still pretty strong, and it's not quite as heavy. You got something to lift there. So you can look at that as an example of how to do a couple of problems you'll see in the classwork. Check out your book. Always check out your book. Read those examples as well. So here's another little demonstration of Cavalieri's principle, where just kind of push the paper in. But I'm done. That's good. You should know what to do at this point with what you see here in your lesson, or what you will see here in the lesson. I hope you do well on it. Let me know in class if you have any questions about the notes, or if you have some questions about the classwork as you work through it. Thank you, and have a good day, everybody.